It's with great pleasure that I get to introduce my friend and colleague today, excuse me, Dr. Runde. Dr. Runde earned his Bachelor's and Master's of Science in Mathematics from the University of Wisconsin and his Ph.D. in Mathematics from the University of South Florida. We've been fortunate enough to have him teaching a variety of math classes here at SCF for about 28 years. And in his spare time has also managed to write a couple textbooks in algebra and liberal arts math, and actually has a new one coming out relatively shortly. Today's presentation is on something that I think that everyone in here can identify with. I think every student has, at one point, has asked this question, and every teacher at some point has had to answer at least a form of this question. And it goes something along the lines of, why do I have to learn this? How am I ever going to use this in real life? What am I actually going to apply this to? And Dr. Runde's presentation today then is going to give us 10 very entertaining and practical applications of various ideas in first year math classes. Now don't worry, I've been assured you don't have to be a math major, you don't have to understand any great mathematical concepts in order to understand and enjoy today's presentation. In fact, he has multiple demonstrations and even some opportunities for audience participation and help to convey these principles. I don't want to give too much away, so please help me in welcoming Dr. Dennis Runde.
All right, thank you very much. This is exciting. I do talks a lot. Most of the time it's full of math teachers, so I'm a little or math students. I give talks every day with math students, I guess. But today I got a normal audience, I guess. So anyway, first regarding the whole thing there, Sue Wire is our graphic artist teacher. I just thought I couldn't have asked for anything better. That's awesome. I know she's not here, but a round of applause for her. Brandon and Hune, thank you very much for doing this series, and Philip Travis is in on that as well. I always say, if you give a teacher a chance to talk, you will be enlightened in some regard or another. So there's been some very nice talks. Hopefully I can live up to those. The first thing, when this came out, I got a lot of questions about that picture. And so I'm going to use this picture to try to get you involved. Hopefully, we have some paper. I gave you some paper earlier.
It's all passed out.
It's all passed out. You could share, if you don't have a piece of paper in front of you, throughout the day, throughout the talk, I'm going to give you a chance to write down something, and then I'll proceed to give the answer. The other thing, too, Brandon referred to it a little bit. I'm not going to make you do any math today. I'll do the math for you. I gave a talk somewhat like this amongst all math teachers. They didn't want to do the math. So I imagine you all, now math teachers, if you want to do the math, you can. I promise you it'll be up here. You can follow along, but you don't have to do it. First thing I want you to look at, though, what on earth possessed me to have this look on my face when this picture was taken? And write down what you think I might have going on in this picture. Be nice. High day, that's a good one. I'll give you a hint. It had something to do with the college. It was out at Lakewood Ranch. Okay, I got to keep this moving right along, so here we go. So we had people from one of the, I believe it was Malt Marine, and Jeff Greeneisen took that picture. I don't think Jeff is here. I don't see him. So he's the only one who may know where that picture came from. So anyway, I wanted to start with that. Now today, I'm going to get some people involved, and I've got some tasks that I want you to do while I continue doing the rest of the talk. Okay, so the first thing I need, I'm going to ask that this gets circulated too. Okay. The sign-in sheet I don't really need.
We need that.
You need that. So if you haven't signed in before you leave, sign up. This is something I want, though. If you haven't put your birthday down, how many of you didn't do this? Okay, I'm going to circulate this around. Put your number down, just the day of your birthday. Okay, you don't have to reveal year or anything like that. Just put make sure your year is on the sheet. If you fill up one, just pass it on to another one, but make sure the date, the day, not the date, is on there. So you'll see that. Second thing, I need a card shuffler, and I need, and we have a volunteer. This is not a new deck. This is the deck I carry around in my backpack. Whenever probability comes up, I use this deck. So it's a well-used deck. Now, every time a new number comes up, you can shuffle it as many times, but every time, just so it's well shuffled, every time the next number clicks up, I want you to shuffle it. Okay? So that's our card shuffle. Now, I need a bean counter. Now, is there any accountants in the room? besides Dr. Proxima? All right. I'm gonna ask our wonderful human resources director. Now, this is a pretty easy task, and you're gonna have to help with me, okay? Because you're sitting here. Okay. Now, this is a checkerboard or a chessboard. What I want you to do, and I'll even help you to start with. So you're gonna put one bean on the first square. You're going to go around this checkerboard, and you're going to put double the number on the next one. And you're going to keep going. You're not going to get very far, though. You're going to run out of room. So I wish I had red solo cups, but I've got blue solo cups. So as you fill up the previous one, just set them off to the side, and keep doubling the number. Okay? Does that work for you? So on this one, you're going to have 2, then 4, then 8, then 16. Okay. Just keep doing it. Right, so then you're going to put those in a solo cup. And then in the next solo cup, you'll put the 32, then 16. Okay, so you're the bean counter. Okay? You got to help. You got to help. Okay, and just keep doing it. You can start doing it right now. Yeah? I need a coin flipper. And I need 2 people, okay? So I'm tossing you a quarter. You get to keep the quarter. All right? Now, you got to do it, though, so I don't hear the quarter hitting the desk every 2 minutes. And you're going to record just the number of heads. But actually, record everything, okay? But all you got to do is flip it, set it down so he can see it, and you're going to record what it is. And then at the end, I'll ask you a question, okay? How many times? As many times as you can. Okay, and then I also need a die roller. So you're up front. You're good. Okay, and you're gonna help. Okay, now he needs paper too. You're gonna keep track of the numbers. Actually, write down each number. In the end, I'm gonna ask you about 6s. So the first one, just write down the 2. Okay, keep doing it as many times as you can. All right. Now, while they're doing that, we're gonna continue on. A few things. Purpose of the talk. The main goal, Brandon really gave us a lot of this already, to share some simple, entertaining, and some cool applications of mathematics. These applications may be used in a variety of math classes, primarily in our first year math classes though. So a lot of intermediate algebra, a lot of liberal arts mathematics. So those are the things that we'll be seeing. The last one, I always like to say when we do something in math class, this isn't rocket science. Well, actually one of these actually is rocket science, so we'll get a little bit of rocket science, but the idea is that simple things, really simple things, can be memorable, can be entertaining, and can really make it more interesting for students. And throughout the talk here, you may see something in common on all 3 of those. Is the word applications, and that's really what we're focusing on today. Now, why is it relevant to how students learn? I don't want to get bogged down in all this, but these are 3 organizations. Thank you. These are 3 organizations, math education organizations, and each one of them has something to say about a lot of things. But in these quotes that I have here, you'll see again, the emphasis of using applications to encourage students and to encourage the learning of mathematics. All right, so here's our first one. How long would it take to visit another solar system? Everybody write down Don't worry, I'm not going to grade them. How long you would think it would take if you keep rolling? Your job is to keep rolling. Now, if we take a spaceship, okay, not a particle of light, good question, but a spaceship, and we just loaded up on the spaceship and headed off to the nearest star, how long would it take us to get there? Okay, so just while you're doing that, just think about that for just a minute. Write down. Okay, I'm going to give you some facts. Proxima Centauri. Okay, scientists, I see a few scientists here. Proxima Centauri is the closest star to our own solar system. It is approximately, that's 39,900 billion kilometers from Earth. Okay, so that's the closest one. Okay, that's the closest one. Now, the question is Alt I just asked, how fast are we going? Okay, the projected fastest space vehicle ever produced will be, should have already happened, but we of course had delays, the Parker Solar Probe. And it's going to launch this summer. And it's projected to travel at 200 kilometers per second. That's about 447,000 miles per hour. Now, if somebody is in the science field, allow me, I'm really stretching this actually. This is actually talking about angular velocity going around either the sun, or for a while it's going to go around Mars. So that's a different kind of velocity than straight line or geodesic, the path that it would take. So just allow me that though, but it's going to go about 200 kilometers per second. So this is a problem you can do in any basic math class, is that you always work with the formula distance equals rate times time. And if you solve that, you get time equals distance divided by rate. We know the distance and we know the rate. That's not that hard to do without a calculator. Okay, and you look at it, it turns out to be a lot of seconds. Okay, that's hundreds, thousands, millions, that's 199.5 billion seconds. When I do this in class, usually I get a response of, yeah, but that's seconds. That's a lot of seconds, but they're little pieces of time. And then you start to realize, to do the math on that, to do the conversion, it's a really nice example of unit conversions. Okay? And it turns out it's 6,326 years. Okay, now, this is always enlightening. That's the closest star, and that's our fastest vehicle. Okay, so when we talk about Star Trek or Star Wars or Star anything, the word science fiction really is the important one there. So I like this one though, because I always get students to, I even asked my nephews a few months ago. We were talking and socializing. And one said, "Oh, about a week." The other said, "No, it's a lot longer than that. It's going to be like 10 years." I guess again. So it's a pretty nice application. Now we can always extend things. On this one, I use this in intermediate algebra all the time when we talk about scientific notation. You can talk about light years. You can really get into the escape velocity. You can really do this. Differential equations really talks about angular boost velocity and space cruising velocity. There's all kinds of different velocities. In math class, I generally don't get into those, but it certainly could be extended in other classes. Now, here's where the title of the talk came from. How cool is that? Write an equation that converts Celsius into Fahrenheit. Anybody remember that one? Write it down if you do. There's some seats right in here. I think I've officially sold out 27,140. I'm excited. Okay, here's some facts. Most people know this one. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit. Boils at 100 degrees Celsius, 212 degrees Fahrenheit. Now, if we know those two facts, we can build the equation. And I really like this too, because this gives students the idea that we don't just always inherit mathematics, we can actually create the mathematics ourselves. And some follow-up questions. Some of you noticed when you walked in, that wasn't just a song that I like. Beds Are Burning, they reference the Western Desert lives and breathes in 45 degrees. I've been using that song in my math classes since I was teaching in Milwaukee in 1988, and I referenced that song. And of course, the people I'm teaching there were like 3 years younger than me, and they're like, whoa, he knows about that song. It's pretty cool. I keep using it. One day it was very enlightening. I was here a few years ago, and a student looks up, oh, that's my dad's favorite song. I'm waiting for somebody to say that's my grandpa's favorite song. So anyway, and then the other question I think is a really nice one too, is what is cold at 40 degrees Celsius or 40 degrees below Fahrenheit? So here's how we approach this. We do ordered pairs. So we do 0, 32, and 10, 100, and 212. We don't even need point slope form for this one. We can use a real simple formula, slope-intercept form. And slope-intercept, or the y-intercept is 32. B is 32, and the slope is a real easy calculation. We'll use 9/5. You just drop it into the formula. And you get F equals MC plus B. There's our formula. The really big thing I like about this is, again, students tell you what the temperatures are. So it's not like you're just handing them the information. People generally know those two numbers, freezing and boiling. And then we build it ourselves instead of just handing them the formula. And then you ask the follow-up question. You plug in there, and 45 degrees is 113 degrees Fahrenheit. Now, as soon as we hear that, we kind of understand, oh, that's a hot temperature. That's very different than what it sounds like. Okay, and then here's the other cool thing. 40 degrees below Celsius is the same as 40 degrees below Fahrenheit. It's the one place on the scale where they are the same. So again, that's surprising. I always get people saying which is colder. By far Fahrenheit. Celsius is these different weird numbers. So now, ways to extend it. Definitely we can use functions. Function notation is a really nice inverse function where you can go from one back and forth. And then it really gets to the point, too, of why Kelvin is needed. Okay, Kelvin is needed because you need a absolute zero. In science, you need that. So there's some good applications. Okay. This one I can't really get you to answer, but I think you know where I'm going with this. How much does a house really cost? And then those of you who are homeowners, how much of that is interest? Now, we'll do a hypothetical. It's pretty accurate. Suppose we purchase a home in Bradenton. Sells for $200,000. The required down payment is 15%. And a 30-year mortgage rate of 4.5% will have a monthly principal and interest payment of 5.06685 per 1,000 borrowed. Now, I give this in the lower level classes, so then they don't have to worry about the heavier formulas that we can use in the upper classes. But this is a pretty nice problem. That's enough information right there. And then we do ignore for this problem. Points, closing costs, taxes, and insurance. It'd be really nice in life if we could avoid all those things too. But for this problem, to keep it simple, we'll ignore those things. So first get the down payment. 15% of 200,000 is 30,000. Subtract that from 200,000, you get $170,000. So you're financing $170,000. You calculate the monthly payment. Okay, so you just take that factor that I gave you before. That number in parentheses is just 170. Okay, you get $861.37 a month. That's pretty accurate. That's an actual mortgage. You tack on the other things you have to pay, but that's people realize. Okay, a lot of times I hear this. That's less than my rent. Okay, and that's a great thing to show students. I love to hear that. You take the down payment and the sum of all the payments, start with the 30,000, just multiply that out, so you end up with $340,093. Okay? So a $200,000 house ended up costing $340,093. Now, I use real numbers, and this used to be a lot more exciting when our interest rates were higher, because it would almost always be over twice the cost of the original house. Now, you know, again, not bad, but still, it's not as shocking when you have the higher interest rates. How much was interest? You just subtract off the original price of the house, and you're paying $140,093 in interest. Okay, now that's assuming you carry the mortgage all the way through to the end, okay, but most people do. So, ways you can extend this problem. We definitely do this in our liberal arts class, where we use a formula or a table, and we can also use a spreadsheet to get the principal and interest payment. Vary the mortgage rate. I do this one in my liberal arts class. I talk about my first house. And I remember my first interest rate was 9.75%. That was in 1991. 9.75%. And I remember calling my dad. I was so excited, and I told him that we're buying a house. And he said, "What rate are you getting it?" I said, 9.75. He goes, "Oh, that's such a great rate." Because before that, everything was double digits. So I was pretty happy it was below double digits. So, but if you do that with the higher rates, it gets interesting. And then Nancy is here. Nancy does a project where they go out and they do all the work, including all of the stuff that we're ignoring for this problem, including mortgage insurance, closing costs, taxes, and homeowners insurance. All right, here's a good one. Does anybody have a quarter-carat diamond? Is anybody wearing a quarter-carat diamond right now?
I actually think I am.
Oh, good.
Pretty sure.
That's awesome.
Yeah.
Really cool. I used to always get a lot of people wearing them. It doesn't happen as much anymore. Maybe they're bigger or whatever. How many now, atoms, diamonds are pure carbon. How many atoms do you suppose are in a diamond? Here, grab a chair.
Thank you.
Write it down. How many atoms do you suppose are in a quarter-carat diamond? I'll give you some facts. Diamonds are made entirely of carbon. A quarter-carat diamond weighs 0.05 grams. So that's, I'm always surprised at that. It seems like it should weigh more, but that's how much it weighs. And here's the giver. They'll give it away. A gram of carbon contains about 5.014 times 10 to the 22nd carbon atoms. This one, okay, I see some calculators out. That's awesome. I love that. That's fantastic. So what we can do with this problem, you can actually do this problem without a calculator. Now, I don't ever recommend that, but it can be done because the scientific notation is pretty simple on it. Again, if you're teaching and taking it, it's pretty simple. You first convert the grams into scientific notation. Then you convert the grams to atoms. Okay? And if you look at that, that's a manageable calculation without a calculator. And that's the whole steps. Now, the answer is there on the bottom. Does anybody want to hazard a guess as how you say that number? Okay, let me help you. Hundreds, thousands, millions, billions, trillions, quadrillions, quintillions. What? Sextillions? Yep. I always find it fascinating that number shows up when we're talking about diamonds, but just a coincidence. But so this is I think this is a pretty cool problem though, because usually, the thing on your finger there has that many carbon atoms in it. I think that's fascinating. A chemistry teacher once told me if you look at a standard text, like any kind of textbook, if you look at the period at the end of the sentence, if you can imagine a ball the size of that period, that ball contains 1 trillion atoms. Okay, so I mean that's just kind of mind-blowing as far as how many atoms are in such a small area or small volume. So here's a really good one too. Any chemistry teachers here? I know some science teachers. Oh, perfect. So the number that I gave you before, you can easily get from the first number is Avogadro's number, and then the second number on the bottom is the atomic mass of carbon. Again, this I would definitely do with a calculator, but again, it's not hard to get that number. And then you can use ratio and proportions. So suppose somebody has a bigger diamond or a smaller diamond, you can do simple ratio and proportions to get the number of atoms there. And then this is always kind of fascinating too. The other forms of carbon, charcoal, and a pencil tip has what? It's not lead. Graphite. Graphite. Yeah, those are all pure carbon forms as well, so you can extend that into there. Now, you guys are being very good. How are we doing with the rolling there? Yeah.
It's a lot of fun.
How about the flipping? You good? You been shuffling?
Yes, sir.
Okay, good. Now, I want to ask before I get started with this, how many of you in the last, let's say, year, how many of you have bought a Florida lottery ticket? That's a lot of people. That's a lot of people. Now, how many people have played poker in the last year? Okay. Of those people playing poker, how many of you have gotten a royal flush in the last year? You did get a royal flush, one. Now, was it dealt to you directly as 5 cards, or was it a hold'em, or where like Texas Hold'em, where you were using the river and all the extra cards? Okay, so that really doesn't apply to what I'm going to show you here. But that's easier. Let's put it this way. That's much easier than what I'm going to show you here. So keep that in mind. Okay, so here we go. How to play. You select 6 natural numbers. You can't pick pi. Ordered 1 to 53. Now the follow-up questions. According to NOAA, National Oceanographic Administration, 300 people each year are struck by lightning out of 326 million people. How many times more likely are you to be struck by lightning than you are to win the Florida lottery? That's a good question. And then, how many times more likely are you to deal a royal flush than you are to win the Florida lottery? So there's another good question. Now, let's just look at this. How we establish the Florida lottery probability. You have 53 numbers, you choose 6. The order does not matter. If you ever see the ping pong balls on TV, they come up in any order, but then when they put them on the bottom, they put them all in ascending order. So the order doesn't matter in which they come up. So this is a classic combination. To win, you must match all 6 numbers. There's only one way to do this. So if we look at this, we see 1, and then the bottom notation is 53, choose 6. And that number is 229567480. I want to show you something on this. I tried to get the Florida lottery website to come up. This did come up in the Google search. Look at the number up there. I guess I got a pointer. Right there, 229578480. It's a little bit wrong. Does anybody know why?
Odds.
Yeah, Kim knows. Okay, it's odds. That's actually the probability. Odds, it should be, the last 2 digits should be 79. I wrote them a letter years ago. never ever heard back from them. But anyway, that's the same number that we see here on the bottom. So your chance of winning the Florida lottery are really tiny. That number in scientific notation, though, is what we're going to use when we do our comparisons. So lightning, your chance of being struck by lightning, 300 out of 326 million. It's about 9.20 times 10 to the negative 7. Now that's a tiny number too, but it's a lot bigger than the other number we have. In fact, how do we compare the two? Well, you divide the bigger number by the smaller number. And again, this turns out, we're doing scientific notation. 21, not 2 or 3 or 4 or 5, 21. You are 21 times more likely to get struck by lightning than you are to win the Florida lottery. I'm taking a little bit of leeway here because not all 326 million of us are equally likely. If you're a farmer or a golfer, if you're outside a lot, you're more likely, but it's close enough. I mean, it gets the point across that we really, I don't worry about getting struck by lightning, but after doing this, I don't worry about winning the Florida lottery. Now, what about the royal flush? Okay, here's where I need my lovely assistant to help me out here. Can you deal me 5 cards, please?
I think we're all hoping it's the one.
Nothing's weird about that.
Than it was to you win the Florida lottery the last time you played. Okay. Now, why do we play the Florida lottery? Why do we play that if we know this? Well, first of all, a lot of people don't know this. Okay. Why do we do it? And you're getting into the next topic is the in mathematics we call it the expectation. And in other words, if she'd have dealt me a royal flush, I might have had a heart attack. But other than that, there was no payout on it. I guess I could have gotten some people gambling on it, but there really wasn't any payout on it. The Florida lottery, there is a payout. That gets into expectation. Now, let's compare this to other rare events. Okay. Oh, you guys are still going. Sorry. Okay. I want to ask you, how many 6s in a row?
In a row?
You look for 6s in a row.
Yeah. Okay.
How many heads in a row? Yeah. What?
I don't know if that's
Weren't you flipping?
Yeah.
I have total.
That's totals. He didn't do.
Oh, you didn't write down heads or
each
tails?
time.
Oh, you just flipped and counted the number?
Oh, no, we have the total number of heads and the total number of tails.
Oh, okay. That's okay.
Start again.
That's okay. The chances of, do you think you did 10 in a row?
There was like 7 tails in a row.
Was there? Okay. That kind of proves my point. That was pretty rare though, right? That was like the biggest strain you had. And that's perfect. So the chances of flipping 10 heads in a row, look at that one. 22,000, almost 23,000, well, no, 22,000 times more likely to do that than you are to win the Florida lottery. 6s? How many 6s did you roll in a row?
At most 3.
At most 3? See, even 5. I just went up to 5 on this one. You're almost 3,000 times more likely. You have 5?
Yeah, he did 5.
Did you do 5?
Yeah.
Oh, wow. Okay. I didn't think it would happen. But that was 3,000 more times more likely than the Florida lottery. All right, so now this last one, oh, wait. Okay, the expectation is the whole thing, is why do you play the Florida lottery? Well, usually you buy a ticket and you dream about what you're going to win with it because there's an expectation that somebody's got to win it, right? Now, what I tell my students is this. Next time they get the urge to buy a lottery ticket, give me the $1 and I'll give them 50 cents back. That way we'll both be 50 cents ahead than what if the ticket had been purchased. So, nobody does that though. So anyway, it's the average of the S&P since 1957 when it was started was about 10%. And it's still about 10%. Even with ups and downs, it has to change quite a bit for that number to change because it's got a long history. You're going to use monthly investments, so we got 12 for N. And then we're going to assume that there's a working age from 25 to 65. So assuming somebody graduates from college, starts a real job at age 25, works for 40 years, and then retires. Now, I want you to write this number down. How much do you think you would have to write or to invest each month during that 40 years for you to be a millionaire the day you retire? I'll give you 30 seconds. Write something down. Write something down. What? Oh boy, okay. Are you out of beans? You guys are out of beans?
Good job, Jennifer.
I actually was going to do that. All right, thank you. You've proven my point more than enough. Okay, so here's what we have. So the follow-up question of the $1 million, how much is interest? That, I love that one too. So here's how we do it. We plug in our values. Okay. We evaluate it. It's $158.13. How close was anybody? Was anybody below that? Was anybody below that? Were you? Okay. Most of the time, people are way above it. Because usually you think, oh, to get $1 million, I got to put more away than that. If you've got a decent, that's manageable. That's reasonable. Follow-up question, if you take that times 12 times 40, that's your principal. That's over the course of those 40 years, that's how much you are investing. Subtract that from $1 million, that's a lot of interest. That's a lot of interest. This is to me, between this and the house, when we do this in liberal arts math class, this is fantastic. I mean, the eyes open up, and then sometimes you get some non-traditional students saying, I wish I'd have known this 5 years ago. You know, and really, it is a fantastic application. Now, to extend it, you can do a whole financial chapter, just all kinds of fun. You can play around with the rates. You can save for other things, college expenses, wedding, major expenses. Saving early versus starting later, that's a really big deal. There's another application where somebody invests for the first 10 years of working and then stops investing, and then just lets that money sit and gather interest till they retire, versus somebody who starts 10 years later and then invests regularly. And the one who gets started earlier, because that money's working for you all that time, you get that benefit. All right, who wants to be really rich? Okay, here's the value of the wheat. Okay, the value of the wheat and the wheat on the chessboard problem. I couldn't find any wheat in the grocery store, so I used red beans. Okay, so here's the epic poem. As a reward, the inventor of chess requested 1 kernel of wheat on the first square of the chessboard, 2 on the second, 4 on the third, 8 on the fourth, and so on, doubling the number of kernels until there was wheat on each of 64 squares. Now, I just gave you guys there's 2 pounds of beans, and we ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got up to 12, 13. We only got up to 13 squares. There's 64 squares on the chessboard. So you start to realize there's a lot of beans on that chessboard. There's a lot of wheat on that chessboard. The poem, too, depending on the source, supposedly the king laughed and said, what a pittance, why are you asking for such a little amount? And then later, he had to relinquish the throne because he couldn't pay off the bet, or pay off the reward. Now, some facts needed. We're going to use wheat, 720,000 kernels of wheat in a bushel. Price of wheat, this is about, as of 2 weeks ago, 4.6025 per bushel. We'll go through this pretty quickly. This is a nice, again, this is in liberal arts math. It's also in pre-calculus math. We do some later in some calculus too, but there's our formula. Starts off with 1, it doubles, and we do it 64 times. So we end up with this many wheat kernels. Now you look at that, it turns out to be 1.18 times 10 to the 14th. $118 trillion. That's worth of wheat on the wheat board. So the story goes that the people, the accountants of the kingdom, knew real quickly this was not going to be a workable solution. So, but anyway, there's a lot of ways you can extend this one. You can use any grains you want. Second half of the chessboard. Anybody in economics here? Any economics people? Economics people? Well, the second half of the chessboard if you're doubling, and this is kind of relevant with the Facebook users, it's in the news right now, is they doubled their users and after a while, you get this massive quantity of whatever, it's unmanageable. And essentially that's the economics model, is that doubling things can't continue. The other good example is bacteria growth and the rapid onset of illness. You can see that with models, because your body is able to fight off an infection, but as soon as it gets to a point where it doubles overnight, you're sick, and you start to show symptoms. That's a real common way. Okay, how weird is that? What is the probability that at least 2 people in a room have the same birthday? Have you ever been in a situation where all of a sudden you talk about birthdays and you're saying, oh, that's my birthday. Well, how weird is that? We both have the same birthday. We have about 80 people in the room here, and we're going to ignore leap day. There's no leap babies here. Assume all 365 days are equally likely. That's not true, by the way. There are certain events that 9 months later, there's a lot of births. You can figure that one out. So we're going to use the number of people in this room. So I'm going to use 80. I'm going to use 80. It's easier to calculate the probability that each person in the room has a different birthday. So if there's 80 of us, it's certainly possible that all 80 of us have different birthdays. Okay? Now, the probability of different birthdays is this. Okay, so you start off with the first one. If I started with my birthday, I have a 100% chance of matching my own birthday. That's where that first one is. Then after that, you have a 364 out of 365 of not matching my of having a different birthday. And then you go around, you keep multiplying these numbers. I'll save but that's what we call a permutation. Okay. Now, if you're trying to do this with a calculator, our standard here is a TI-83 or a TI-84. You can't do this problem for anything above 39. So the probability of at least 2 birthdays, so this is the number I'm going to calculate. So to do this, let's see if I can do this quickly. I've got a calculator here. So I think you can see up here, you can see where I'm waving. So I'm going to go 1 minus, and I'm going to do a permutation, so that's NPR. I have to go in here, and I'm going to go 365, and then 80. Okay, and then I'm going to divide that number by 365 raised to the 80th power. Okay. Now, what do you think the probability of there being 2 birthdays in here is? Like, what percentage do you think it's going to be? 70%? 80%? Now it's calculating. Okay, it's right down here. It's really tiny. Okay, there's a 99.9914% chance that at least 2 people in this room have the same birthday. So, did my birthday sheets come back around? Yes. Now, this is, I don't even think everybody did this. Oh, goodness. Okay. Just glancing through this real quickly, there are 3 people who share the same birthday. And this is really, really cool. There's 3 people whose birthday is today. Raise your hand if it's your birthday today. 1, 2. Okay, somebody else didn't understand the direction. Happy birthday, I don't want to spend time, but happy birthday, that's awesome. So that's not that unusual when you get a big group of people that 2 people are going to have the same birthday. And in fact, it's a pretty good problem in one of our stat books where you talk about what's the number of people you have to have so it's more than 50-50. And it's about 30. If you have 30 people in a room, it's better likely than not, that you'll have 2 people with the same birthday. So I do that in class, and about half the time you get, because that's about the size of our class, is about 30. So anyway, back to the show here. You can extend the problem. What about this? How many people would we have to have in this room to guarantee that 2 people have the same birthday? 367, really, right? If you do go back and include leap day. Does anybody know what that's called? That's called the pigeonhole principle. And that's used quite often in higher level mathematics where you have, it doesn't seem like a big deal, but if you have n things and n plus 1 to put into those n things, you got to double up somewhere. And that's a nice principle to talk about. The equally likely thing, I'll save that. There's a chart. You can see where the peaks and valleys are from birthdays following. Again, it's after Christmas, after holidays, essentially. 9 months after holidays, there's a lot of babies born. So, okay. Now, real quick, I'm going to keep going. I got it this one. If a person wanted to visit all 50 state capitals and return to D.C., how long would it take to find the shortest route? Too long is right. Okay. So just think about this. So, well, here's some assumptions. This is what we call a traveling salesman problem. We're referencing the brute force method to find the optimal solution. A 51 by 51 matrix of the distances between all 51 capitals would be entered into the world's fastest computer. Okay, so we're talking about the fastest computer on Earth doing this problem. How long do you think it would take to find the shortest route? Just write that down. How long would it take that fastest computer to find the shortest route? Okay. As of a couple weeks ago, China's Sunway Taihu Light, I guess, it can perform. This is 93 petaflops. Every 6 months they upgrade. There's a list, top 500 computers on Earth as far as how fast they are. So here's what we do. There's 50 factorial. So 50 times 49 times 48 all the way down to 1. You multiply those out. Each route in its reverse would have identical distances though. So if you go around it clockwise versus counterclockwise, those two are really the same route. They have the same distances, so we don't have to count all of them, so we divide by 2. So we have 50 factorial over 2 different routes. Each route has 51 operations. Okay, think about that, because you have to go from DC to the first, to the second, to the third, to the fourth, all the way around to all 50, and you got to come back to DC. So there's 51 calculations per route. So we have this, which again, that's a lot of operations, but we're going to let the world's fastest computer work on it. Okay? So 1 second, you can do 9.3 times 10 to the 16 operations. Just to give you a hint, I threw in there that 1 year has a lot of seconds in it. I threw that in there. That's 2.64 times 10 to the 41st years. Now let's look at that number written out. Okay, my slide didn't hold all the zeros. Does anybody want to say that number? Don't try. That one's a long one. That's 264 duodecillion years. That's our fastest computer. Okay. Now, here's the thing. I love to do this. Liberal arts class, we talk about traveling salesman problem, and everybody wants to know at the end of the semester, hey, do you have any extra credit? And I say, no, don't. But it is a fascinating problem. Now, what it immediately says, the brute force method is very impractical. Okay, you can do better than the brute force method. Even in our textbooks, we talk about the nearest neighbor. It gives you a pretty good route. It doesn't give you the best one, but it'll give you a pretty good route. And then here's what I love. In mathematics, we often have a problem that we can talk to you for about a minute and you'll understand what the problem is. That's understanding what the problem is asking. But now attacking the problem and doing the problem is a whole different animal. Okay? Real quickly, last one, 2 minutes. Okay. Do you believe in magic? Fill in the magic square. I'll give you 30 seconds to do this. There's 9 boxes. Fill in the numbers 1 through 9. Each row, column, and diagonal must have the same sum. Now, if you've taught liberal arts lately, just sit and smile and be smug. So you know how to do this. All right, we're almost out of time, so I'm gonna jump in. So, and the PowerPoint doesn't lend itself nicely to this. So, what you essentially do is you start with the two end numbers and your middle number, and you put those in a row or column. Put them anywhere, but the middle number has to go in that middle square. Once you do that, so you put 1, 5, and 9 in the middle, then you pick the next two extremes, the 2 and the 8. Oh, and 1, 5, 9 gives you a sum of 15. So then you go 2 and 8. The only way 2 and 8 is going to add up to 15 with the 5 is if we put them this way, because if I put the 8 above the 9, that column will have 17. It's too big. Once you get those in, it's just to fill in the blank then. Now, this is a classic math thing where, how many of you knew how to do that? How many of you did it in the 30 seconds? Besides Nancy and Kim. Okay. But now that you know how to do it, I could give you another set of numbers and you could do it. Okay, right? I mean, that's a big part of problem solving or a big part of expertise. Somebody will say, well, how do you know how to do that? Well, I've been doing this 28 years. That's how I know how to do it. And how are you going to know how to do it? You're going to do your homework. You know? So that's the whole point. So, all right. You can extend this problem. There's lots of ways you can extend magic shapes, other shapes. And there's my sources up on the board there, along with some websites. And then here's your part.